make it less dark here, but I think this is all I got. Okay, so this is Chapter 10, Probability. The information in this lesson can also be found in Section 2 in Chapter 10 and Section 6 about odds. So we're going to talk about the fundamental counting principle, and then we're going to figure out how odds are different than probabilities and use conversion to go back and forth between them. They're very similar, just not the same, okay? Let's start with the FCP. When an outcome of an experiment is composed of a series of events, the fundamental counting principle helps one count the number of possible outcomes in larger sample spaces, or for those by more complicated events. You don't want to start making tree diagrams for complicated things. It gets too unwieldy and it doesn't help. So there are ways to just do it a lot simpler. If I can find my pencil, I will do it. Here it is. So for example, pizza place serves pizza with your choice of 10 different vegetable toppings, 5 meat toppings, 3 cheese toppings, 3 types of crust. That's a lot of different pizzas. All right, I'm not going to make a tree diagram for that. What I can do is take the number of choices for the vegetables times the number of choices for all the different categories and so on. So this is going to be 10 times 5 times 3 times 3. That's going to give me 450 different kinds of pizzas I can order at this place. Okay. Example 2, there are 4 wires, red, green, blue, and yellow, needed to be attached to a circuit board. A robotic device will attach the wires. The wires can be attached in any order, and the production manager wishes to determine how many different ways 4 wires can be attached so he can program the computer. Okay? So there are 4 different wires, so 4 choices for the robot to choose for the first attachment. So the robot arm reaches out and he has 4 to choose from. Okay, that gets attached. Then when he reaches out again, there's only 3 available to be attached. 3 choices, 3 different ones. Okay, attaches that, goes back. There's 2 different ones to choose from. So these are choices to be made. I don't know if you can see it up there. Number of choices. So number of choices times number of choices times number of choices. When it goes back, there's 1. You can put the 1 on there or not. It's pretty obvious. So when you kind of go in an order from a number all the way down one at a time to a 1, that's called a factorial. So like 10 factorial would be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You have to go all the way down to 1 to get a factorial. And that is a button on your calculator. And it implies multiplication. But anyway, those numbers multiplied together is 24 different ways this robot, different ways, different orders of can be attached. Okay. So let's do the practice at the bottom here. In one state, the license plates can be made with a combination of 3 letters. So 1, 2, 3 letters. These are going to be choices. So I want to be able to multiply them together, and 3 digits. What's a digit? A digit is a number from 0 to 9. So how many digits are there? There are 10 digits because it includes the 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 digits from 0 to 9. Okay. Letters of the alphabet, 26 letters in the alphabet. Okay. So we want to make license plates that have 6 places in them. Okay. If the state has about 6 million cars, will this plan be enough for different plates for every car? May assume repeats are allowed, if not specifically disallowed. So repeated, replaced, put back makes a big difference. But this one, you can repeatedly use numbers again. You could use AAA, and that's okay. So when we put letters down, how many different letters do we choose from on the first choice? Okay. The second choice, you can still choose the same as you got on the first one. Third choice, same as you got on the third choice. And then digits, all 10 are available, all 10 are available, all 10 are available because you can use them more than once. All right, so when you multiply all that together, you get 17,576,000 different possible license plates. So surely you have enough for 6 million cars. Okay? But in a password that has 5 digits, 1, 2, 3, 4, 5, and 2 letters, 1, 2. So this is a 7 places password, okay, that has 5 digits, 2 letters without replacement or repetition, okay? So that means once you use one, you can't use it again. So in the first digit, we have, when we're making up this password, we have 10 different digits to choose from, 0 through 9. But then once we use one, we only have 9 left to choose from because you cannot repeat them. And then when I choose that, and I choose that, so I'm using different ones, okay? Fifth one, 6, only 6 choices left out of 0 through 9 because I've used the other ones once, okay? And then the letters, I have 26 letters to pick from on the first letter I choose. The second letter can't be the same, so I only have 25 to choose from. So for example, I could choose a sample password would be what, a 7, a 2, a 3, a 5, a 0, an A, and a P, okay? No repeats, 5 digits, 2 letters. So how many different combinations of passwords could I come up with? Well, if I multiply all these together, I get 2,808,000 different combinations. That's why nobody can guess a password if it's like that. Okay? And then the last one, there are 15 candidates for position of president, vice president, secretary, and treasurer. How many different results can there be in the election for these 4 candidates out of 15? So it doesn't matter whether you're starting with treasurer or starting with president, one person will get picked for one spot. Out of, think of names in a hat. You draw one name out. Okay, there are 14 left to choose from on the second pick. Take that name out. Okay, these are people, so they can't hold more than one position. So as you pick treasurer, secretary, president, it takes names out of a hat. Okay, so we only need 4 positions. So there are, at the end, 11 people that didn't get chosen for anything. That makes sense because there's only 4 positions. But the different ways they can be chosen, 32,760. If you only had 5 candidates, if only 5 people stepped up, this is another example. So the first person could be a 5 choices, right? Names in a hat. Second person pulls out, third person pulls out, fourth person gets pulled out. That's the same as 5 factorial or 120. But there were 15, so they didn't all get a position. Okay.